Hello students, how are you? I hope you all are good. So today in this lecture we are going to discuss about static condensation. So let us see what is static condensation, and with an example we will try to understand the concept of this static condensation along with that equation. Also how we will get that equation, derivation of the equation also we will see, right? So let us start static condensation. Static condensation means nothing. It is a technique to reduce the number of degree of freedom or displacement in an analysis. It is actually performing part of solution before assembling the system. Okay. So first let us see this first part, that is it is used to reduce the number of degree of freedom or displacement in an analysis. Suppose we have a structure in which degree of freedom is 10 or 12. Let us say 12. Out of that, we want only two values. Out of that, only we want two values. So for finding that two values, if we have a degree of freedom of 12, we will have a size of a stiffness matrix 12. If the V is displacement field, if the displacement is 12, the size of a stiffness matrix is going to be 12 by 12. But we want only, suppose D1, D2, D3 is there, we want only D1 and D2. So if we want D1 and D2, actually it should be of 2 by 2. Right? If there is only two displacement, that stiffness matrix is going to be 2 by 2. So see here, we need to solve for finding D1, D2 only. We need to solve this 12 by 12 matrix. And it will use this static condensation. We will solve this 2 by 2 and we'll get the value. So how we will do this? So in this, two terms will come: retained degree of freedom and condensed degree of freedom. Condensed out, rather I can say condensed out degree of freedom. These things you need to understand, because here what we do, let us take an example. This is an example. There are 4 degree of freedom: D1, D2, D3, D4. Out of that, we want only this D1 and D2. So what we will do, we will retain the D1 and D2 and we will condense out D3 and D4 like this. You can see here D1, D2, we will remain it. D1, D2, retained degree of freedom, and we have removed that D3 and D4, that is condensed out. So what we call it as D3 and D4 in this case is degree of freedom to be condensed out and represented by C. Degree of freedom to be condensed out represented by C. Whereas this D1 and D2 are the retained degree of freedom represented as R. So in this example, we have 4 degree of freedom. Out of that, we want only D1 and D2 value. That will be called as retained degree of freedom. And apart from that, D1 and D2, D3 and D4 will be condensed out. That is called as degree of freedom to be condensed out represented by C. So now our new structure, you can see D1, D2, and we have removed this D3, D4. Okay. So now we will write this stiffness. We know this F is equal to K into delta, right? This is nothing, K matrix. This is delta matrix. This is F. So we know this equation F is equal to K into delta. This matrix form. Okay. So let us write this in this form. F is equal to K into delta. Now this stiffness matrix, if you will see this original form, then it will be of size 4 by 4 matrix. So what I have done, I have just reduced this. Means KRR, if you will see KRR, what does it mean KRR? KRR means nothing, retained degree of, stiffness of retained degree due to retained degree of. What does it mean? Suppose if you are finding a stiffness as 1, let us say this as 1, this is as 2, and here there will be 3 and 4, right? 3 and 4, because both are here only that we have condensed. So if you are going to find the stiffness at 1 due to 1 only or due to 2, what will happen? Both are retained degree of freedom. So the stiffness matrix we can represent it as KRR. RR, both the terms means where you are finding and due to which force or which degree of freedom you are finding, both are retained degree of freedom, then it is called as KRR. KRC means where you are finding and due to which. One is retained degree of freedom, another is condensed out degree of freedom. Then it is KRC. Similarly, it will be KCR also, and finally it will be KC. Stiffness due to condensed out degree of freedom at condensed out degree of freedom. Means both. Means suppose if you are finding stiffness as 3 due to 3, K33, that is actually KC, because 3 is condensed out degree of freedom. K34 if you are finding, that is also condensed degree of freedom. K44 if you are finding, that is also condensed degree of freedom, right? So that will be KCC. These all will be represented as KCC. Means if you are finding K33, in this case, in this example, K34, K43, and K44. These all are represented as A, C, C. Similarly, if you are finding K11, K12, K21, K22, that will be KR. So this is KCC, KRR. Retained means whatever the retained is there, 1 and 2, so we are finding a stiffness at that point due to the retained degree of it. KRC means we are finding at retained due to condensed out. So similarly, we can suppose if you are finding at 1 due to K1. K1. Okay. So here you can see 1. 1 is retained and 3. 3 is what? Condensed. So KRC, this is KR, right? Similarly, it can be written as K1, 4 also. Similarly, K23, K24. So these all are I have represented as KRC. Similarly, KCR. So if you will internally see, then how many elements are there in KCC? 4 elements. 4 elements means matrix of size 2 by 2. So this is of size 2 by 2. Similarly, this is also of size 2 by 2. This is also of size 2 by 2. And this is also of size 2 by 2. Now the question is why all these are of size 2 by 2? Because we have condensed out 2 degree of freedom and we have retained 2 degree of freedom. Suppose in any case 3 degree of freedom are there and you have retained 1 degree of freedom and you have condensed out 2 degree of freedom, then what is going to happen? Then in that case KRR will be of size 1 by 1, KCC will be of size 2 by 2, right? According to that you have to see the sizes. So here the sizes are going to be 2 by 2 only. Why? Already we have discussed. So if you will write here all the 2 by 2 matrices, what will be the final size of this matrix? Just imagine what will be the final size. Here 2 by 2 means 4 elements will come. Here 2 by 2 means 4 elements will come. Means can write here, suppose 1, 2, 3, 4 elements. Okay. Just see, this is your KR. Now again KRC also 2 by 2. So 1, 2, 3, 4. KRC. Again 2 by 2. 1, 2, 3, 4. KCR. Then again 2 by 2. 1, 2, 3, 4. KCC. What is the final size of the matrix if you will add? This is row 1, row 2, row 3, row 4, column 1, column 2, column 3, column 4. So this is finally 4 by 4 matrix that we should get because there is 4 degree of freedom, right? Here degree of freedom is 4. So stiffness matrix will be of also size 2 by 4 by 4. This is 4 by 2, 4 by 2. So same here we also getting this 4 by 4. Just we have represented this in the format of KRR, KRC, KCC, KCR. Nothing new. This is completely a stiffness matrix of the given structure itself. But out of that we have divided into 4 parts, which are to be retained, which are to be condensed out. According to that we have divided, right? And that is easy to find also because you can see here what are the condensed degree of freedom, what are the retained degree of freedom. These things you can see by in the given question itself. It will give you which are going to be condensed out or which are going to be retained. Into UR in UC. UR UC what? UR will be the retained displacement at retained degree of freedom, and UC is the displacement at condensed out degree of freedom. So UR, how many UR will be there? Means at UR there will be two displacements. How much? UR means retained. Retained is 1 and 2. So here will be U1, U2. In place of UC, you can write U3, U4. So how many size? What will be the size? The size is going to be here 4 elements will come, right? U1, U2. That will be your UR. So UR is nothing. U1, U2, and UC condensed out is U3, U4. So 4 are right. 4 by 4 matrix. Obviously here 4 elements would come. And similarly 4 FR, FC. So in FR also again same. FR also we will have the same thing. In FR we will have force at 1, force at 2, and FC we will have force at 3, force at 4. So this is also 4 elements. Again. So whatever this matrix I have represented, this is the same matrix as we are discussing from the basics of this finite element. From the starting itself, the stiffness matrix should be of size this by this. By seeing the problem itself, we can test. Same thing is there. Just what we are doing, we are dividing that into a particular term, that is KRR, KRC, KCR, KCC, UR, UC, FR, FC. It is a normal problem only. In a normal problem, if they are asking you to find the displacement at this, you can use this concept of static condensation by finding whole the processes, stiffness matrices. If they are asking you to find this and this, then you can divide that stiffness matrix in this format: KRR, KRC, KCR, KCC, according to the question, right? Now, from here we can write equation number 1 as KRR into UR plus KRC into UC will be equal to FR. Similarly, we can use this here: KCR into UR, again KCC into UC is equal to FR. So here I have it, right? Wherever R is there, retained; wherever C is there, condensed. So from this equation number 2, can we find this UC value? Can we find this UC value? Yes. Keeping this UC value, so let us see if I am transferring this UC value this side. So here it will come FC. So KCR, what will happen here? Can I write this in this form? KCR into UR can be minus F of C, can be written as minus KCC into UC, right? So from here UC value. These all are matrices, right? So once UC value will be now 1 by minus KCC, okay, into KCR into UR minus F. Now 1 by minus of KCC. What does it mean? 1 by matrix of something. If we are writing 1 by a matrix, what we can write it as? A, right? Can write it as 1 by A. If you are writing, we can write it as A. Okay. So here just I have given minus KCC inverse, minus KCC to the power minus. So this we have got from this equation number 2. So what we will do now? Whatever this UC value we got from equation number 2, we will put in this equation number 1 here. We are going to replace this UC value here. So what we will get? Let us see now. So if you will replace it, we will get this equation KRR minus KRC into KCC inverse into KCR into UR is equal to FR minus KRC into KCC inverse into FC. Just this value we have got from this equation number 1. Just putting the UC value. Once you put this UC value here, we can find this value, right? So we got this value. Now here this stiffness, you can see these all are of stiffness term, right? So we can write as KC, that is condensed stiffness matrix. K, this is C, upside, right? KC, not KC, that is upper side. So condensed stiffness matrix. Here we can write this term as FC, that is condensed force vector. So I can write here K of C into UR can be written as F of C, right? So this K of C will be size, what size? 2 by 2 matrix. This is going to be 2 by 2 because what I said initially, in place of this 4 by 4 matrix, we need only two displacements. So we are going to reduce this 4 by 4 matrix into 2 by 2 matrix so that our calculation will be easy. This is just a problem. You can say, sir, 4 by 4 matrix solving and 2 by 2 matrix almost okay. We can solve 4 by 4 also. Yeah, you can solve. But this is just an example. Basically, this is used when the degree of freedom is going to be 8, when the degree of freedom is going to be 6, when the degree of freedom is going to be 12, 15, 20. Out of that, you want only 3 or 4 degree of freedom. So what you will do there? You will solve that 20 by 20 matrix. It is going to be long period and long time, taking long time to solve that problem, even that lengthy and all. So it will be very difficult, very clumsy calculation. So in place of that, we can use this technique concept to reduce that stiffness matrix to the desired size, how much we want, right? Actually, it depends upon the unknown degree of freedom. What are the unknown degree of freedom? What are the degree of freedom to be retained? So K of C into UR. UR is the displacement at retained degree of freedom. That is U2 here, sorry, U1 and U2 is equal to F of C. F of C you will get from here. That will be of size 2 into 1. So from here, whatever the unknown UR, in this case, unknown is U1 and U2. You will be able to find this U1 and U2 by using this equation. So this is all about the static condensation. This is all about static condensation. This is the approach of static condensation. So what is the use of that static condensation? To solve or to analyze a structure having more degree of freedom, and we want only a particular displacement. We want only a particular displacement. Then what we will do? We will condense out the displacements which are not required, and we will retain the degree of freedom, or we will retain the displacement which we want, and then we will reduce the matrix according to that retained degree of freedom, and then we will find the retained displacement. This is all about the static condensation. Here I have written one thing. This K of C describes behavior of whole structure with only these 2 degree of freedom. What does it mean? This K of C will describe the behavior of whole structure by only these 2 degree of freedom. This is why I have given the definition itself. It is actually performing part of solution before assembling the system of the equation. Performing part means here the whole degree, whole structure is going to be described by only this K of C. Even though here the degree of freedom is only 2, since the total degree of freedom is 4, but in this case we have taken only 2 degree of freedom. Still, this will describe the whole structure, because why it will describe? Once you get this UR value, then if you will put this UR value in equation number 3, we will get UC value. But this is your equation. If you will put this UR value here, whatever the UR value you got, you are going to get this UC value, which we have already condensed out, right? Still, there is a provision. If you have calculated UR, you can find UC also by using this equation. This process is known as recovery. This process is known as recovery. So in a static condensation, what is recovery? Recovery is nothing. Once we get the retained degree of freedom, once we get the retained displacement, if we'll put that retained displacement in that equation number 3, that equation, then we can find the condensed degree of freedom or condensed displacement also. This process is called as recovery. So this is all about static condensation. So you should know what is the definition of static condensation. Definition means what is a static condensation, how to use this static condensation. So example also I have given. With that example, I have derived the equation also. So derivation of equation you should understand. Along with that, what does it mean? Recovery. What does recovery mean? So these things are important. All about this is all about the static condensation. You can use this concept anywhere, wherever the degree of freedom is more, and out of that only we desire any particular displacement. So whatever the problem we have discussed in the finite element, suppose some CST element is there. So there will be 6 degree of freedom, right? So out of that 6 degree of freedom, we can even asking you only 3 degree of freedom. Suppose U1, V1, U2, V2, U3, V3 is there. They are asking U1, U2, U3. They are not asking V1, V2, V3. So what we can do? We can take U1, U2, U3 as retained degree of freedom and V1, V2, V3 as condensed degree of freedom. And by using this concept, we can find the U1, U2, U3 by reduced matrix of size 3 by 3. Okay. So thank you everyone.